Hello everyone, I'm Norman Wahlberger, and thanks for joining me on this exploration of research level mathematics. We are looking at solving polynomial equations, very classical subject, in a potentially new way. So last time we were looking at the quadratic equation, and we wrote it as t plus c1x plus c2x squared equals 0, and we got these two solutions, x1 and x2, through a method of a kind of a power series method, proceeding step by step, solving some equations. So we have a power series in t here with coefficients which are little functions of c1 and c2. And then there's also these numbers which are the Catalan numbers. C of n is 1 over n plus 1 times the binomial coefficient 2n, choose n. And we had two solutions. The second one a little bit more complicated than the first one due to this additional sort of constant term. But otherwise, actually, they're very similar. This was just sort of the negative of this one here. Okay, so what we want to do today is we want to wrap up this quadratic case and move to the cubic case, which is a lot more challenging. Okay, so I want to rewrite this x1 as, well, in terms of more sort of standard mathematical notation involving summation. So let's rewrite, there it is, as the summation, okay, x1 equals, so there's going to be, well, there's a minus sign, let's pull that out, and then there's a summation sign, and maybe we'll use the dummy variable k. So k is going to go, say, from 1. 1 will be the exponent of t. So k goes starting from 1. And this k is going up to 9. Okay, and what are we actually doing? Well, there's a power of t, so t to the k. And then in front of that, there's some coefficients. There's, first of all, a Catalan number. And so we decided that 42 was the fifth one, fifth Catalan number. And so that's corresponding to the t to the sixth term. So probably we should put ck minus 1 here. All right. And then there's also this quotient of c's. So there's some power of c sub 2 on the top and some power of c sub 1 on the bottom. Let's figure out what these powers are. So in case, say here, when k is 2, then the power of c2 is 1 less. And that's carrying on. The power of c2 is always 1 less than the power of t. So we should put up here the exponent k minus 1. And what about the denominator? There's power of c1. They are all odd powers. So the power here should be 2 to the something minus 1 or plus 1. Say 2 to the k. In case k is 3, we're going to get a power of 5. So we should choose 2 times k minus 1, it looks like. All right. And let's just check that. Let's see what we have in the way of definitions. So we have cn, right? And these ones we don't care about. So let's just evaluate this thing. And just compare minus t over c1 minus t squared, c2, c1 cubed. So scientific workplace arranges the terms here a little bit differently from what we've got, but it's the same. And the last one, 1430, t to the 9, c2 to the 8th, divided by c1 to the 17th. That looks like a good formula. Okay, what about our x2? Well, that was much the same. So it was really the negative of what we got up here. So we should just put that without a negative sign this time. And then we should throw in this additional constant term, minus c1 over c2. We'll put that out front with a plus sign. And we'll check that. Okay, what's that? Evaluate. Do we get the same thing? Oh, here's the minus c1, c2. Okay, we can move it over there if we prefer. And then otherwise it looks much the same as this. Okay, so that's for going up to sort of level 9 or degree 9. And in general, we like to write, well, we want to write some more general formula. So we'll write x1 equals this thing here. And instead of having a 9, I'll just put a plus sign, which is my way of indicating that we have on series. Okay, series which are ongoing. But we are definitely not pretending that we are summing all of these things to infinity. Absolutely not. Okay, that's an arithmetic that's not allowed in proper thinking, despite the fact that it's commonplace in modern pure mathematics. A very sad story. Okay, so we're not pretending that this is an expression, okay, which is something like a polynomial or a polynumber, but it has an additional aspect, and ultimately we'll have to describe, how the arithmetic of such things work. But crucially, that arithmetic is going to be finitely specifiable and finitely checkable. Okay, that's the crucial distinction here. Okay, and there's also, of course, the other one, that's x2. There it is there. And we should go up instead of to 9. We'll just keep on going. Okay, and just a note. So, eventually we will interpret these once we have proven this formula, or these formulas, in some kind of truncated algebra of on series. Okay, but we're just exploring right now, so we don't have to nail everything down. We just want to get some formulas and then stare at them and contemplate them. But right now we have some really nice formulas for the quadratic case. And I do want to emphasize that we have not yet proven these. So what we've done is we've made some calculations going up to degree 5, up to degree 9. And certainly those calculations suggest some kind of general formula like this, but it's still a question to be proven, okay? And those of you with some mathematical experience will be able to prove them, okay? So you may want to sort of delve into just proving these things without any reference to the usual classical formula, the quadratic formula, just starting with algebra, and of course, employing properties of the Catalan numbers because they're central objects in this story. Fabulous. Okay, now it's time to move on to the cubic case. Okay, the cubic case. So here is our general cubic equation. T plus c1x plus c2x squared plus c3x cubed equals 0. Where again, we're using t instead of c0 because we're going to follow the rather successful road that we traveled down with our quadratic case, where we're going to expand things in powers of t. And we are going to solve this for x, hopefully. And maybe you will try the same kind of story. We'll just write x as some unknown power series in t, and we'll choose, say, going up to degree 7, a little bit more than 5, but less than 9, so it's a compromise. And we'll see what happens when we plug this thing into this equation and see if we can find out what the AIs are in terms of the C's. Okay, so there's a condition here, so subject to the condition that t to the 8 equals 0, we want to solve for let's say, the A sub i's in terms of C1, C2, and C3. Okay, are we ready to do that? Okay, let's have a look. So here we'll take t plus c1x plus c2x squared plus c3x cubed, okay, and we'll write it again. And now we're going to replace the x here with this expression. Okay, and we'll just copy this thing, and I'll put it here, and I'll also put it here. Okay, let's expand this whole thing. So it's got cubic terms, so there'll be lots of terms. I just want to show you what that actually looks like. So let's expand this out. To give you a sense of the power of these kinds of programs. Okay, it's absolutely fabulous what they can do with polynomial arithmetic. And that's absolutely crucial if you're an amateur mathematician wanting to do experimentation exploration in mathematics. You have to deal with polynomials and matrices. Those are the main kinds of arithmetic that go beyond our usual arithmetic of numbers. Okay, so polynomial arithmetic, matrix arithmetic, those are your two fundamental arithmetical tools. Okay, and that's pretty well it, people. You know, it really doesn't get much more than that. I know there's all these fancy things, but ultimately they come down to those two things. Okay, so that's all too much, isn't it? Right, so we are going to shortly remove this, but I'm going to truncate this, right? Because we've agreed that t to the 8 is 0. So a lot of these terms here, like this one here with t12. So I'm not going to go through individually and kill them. I'm going to just use our power series little tool. Okay, so we're going to expand this number of terms. Let's say 8 powers of t. Okay, what do we get? Okay, there's the equal sign. We look for the equal sign. Okay, this is the stuff that we had before, and I'm now about to selectively delete that. Delete it. And now let's have a look at what we've got here in front of us. The OTA, that means that there's terms of degree 8 above that. Okay, so what we see is a constant term, a multiple of t, a multiple of t squared, all the way down to a multiple of t to the 7. Now, what do we have to do? Well, we have to set all of this equal to 0. So we'll put up here. So we get 0. 0 equals all of this stuff. That's a polynomial in t of degree 7. All the terms, all the coefficients had better be 0. So this gives us a number of equations. Okay, and we'll write them down just like we did before. So this first one is the constant term. And while we're at it, we're going to factor that thing. That's the same thing that we did in the quadratic case. And that's going to be 0. In fact, I'll just write it like that, okay? And then we'll write down the other ones, and then we'll stare at it. Okay, and then there's t, coefficient of that is 0. So this first equation allows us, potentially at least, to solve for a0. Okay, and you see what's involved in doing that. There's two possibilities. a0 is going to be 0 from this factor, or a0 is going to be a solution to this quadratic equation. It's a quadratic equation. It's written a bit funny. Let me just write it a little bit more smoothly. Put the linear term there. It's c1 plus a0 c2 plus a0 squared c3. So it's a quadratic equation with constant terms c1, and then c2, and then c3. So do we know how to solve quadratic equations? Well, yes, we do, because we've just done that. Okay. So in principle, we could write down a solution for a0 from this factor, but it'd be a lot simpler if we wrote down the other solution, which is that a0 equals 0. So again, there's going to be this separation into these two cases. The simple case is when a0 is 0, and the more complicated case is when this factor is 0. Okay, what are the other ones? Okay, anyway, oh yes, and so by the time we've sort of decided on what a0 is, then this next equation that we've just written down, let's have a look at it. As an equation in the a's, there's an a1 here, there's an a0, there's an a1 here, an a0, and a1. So this is a linear equation in a1 that has an a0 involved. So if we've already got a value for a0, we can simply solve this equation because it's a linear equation in a1. Okay, and then the next one is this thing here, equals 0. And then the cubic one. And then the degree 4 one. These are getting a bit longer, aren't they? The degree 5 one. The degree 6 one. Okay, we're just almost at the limits of visibility here. And let's see this one here. And just to make it temporarily visible, I put a line break in there. So that's that one there. Okay, what are we going to do? We want to solve this for A0, A1, A2, up to A7. So I'm actually going to go back up to my earlier work, where at some point I wrote down a list of the AIs. I'm just going to borrow that again. So let's just copy that. Come back down. Okay, let's get rid of this. And I'll put these A's here. Okay, so let's solve this. I'm going to first copy this and put it, and also there. So just another copy. So this first one, we're going to do the simplest thing. Okay, the simplest thing is to agree that A0 is actually equal to 0. A sub 0 equals 0. Okay, so let's start with the possibility, or the case A sub 0 equals 0. All right, so that's included there. So this A0, okay, this one is then redundant, but it doesn't matter. And then we'll be able to, or the computer will be able to, successively solve for A1. And then this next one has an A2 in it, which is appearing only linearly. And then the other things are A1 and A0. And then the next one has an A3, which is appearing linearly, and so on. So it should be a snap for the computer to solve each one of these sequentially. And to make sure that it doesn't mess up, I'm going to put this back as a one-line thing, even though you can't see it. But it doesn't matter, because we're just going to ask the computer to solve this. Compute. Solve. Oh, I have to, before I do that, I should copy this. We're going to solve A0 up to A7, because the last term is A7. Okay, now I have to put the cursor back in here somewhere. Anywhere, it doesn't matter. And now I'm going to ask our brilliant friend to solve for A0 up to A7. Okay, you can do it. Okay, let's see what happens here. We get something here. And I'll get rid of the brackets. And maybe I'll get rid of the solution. And so we can see this. Maybe I will put it a little bit more organized way, so we can kind of see them sequentially. A3. We can see this is actually quite a lot more involved / interesting than the quadratic case. Right? Remember, in the quadratic cases, all these a's turned out to be so some power of C2 divided by some power of C1, and it was rather predictable. Okay, it's suddenly not so predictable at all. These AIs are now polynomials in the C1, C2, C3, with also denominators. The denominators are powers of C1. Actually, that is very familiar. Okay, but there's then these other terms. And now if we actually stare at this for a second, you say, but wait a minute, actually we see something that we recognize already. Have a look, see if you can see what we've already seen before. You see that the coefficients, if you just look down this first column here, where the terms involved are just pure powers of C2, we're getting 2, 5, well, 1, 1, 1, 1, 2, 5, 14, 42, 132. We recognize the Catalan numbers. So this is just what we've already gotten before. And then there are some additional terms that also involve C3. So we note that this extends the quadratic solution in that if we set C sub 3 equal to 0, in other words, if we reduce the equation from being a cubic to a quadratic, then all these other terms will disappear and we'll just get what we got before. We get what we got before. Okay, so great. Now we can write down some kind of solution in the same kind of way that we did in the quadratic case. So let's go back up to our expression for x. Here it is here. And we get a solution, x1, say. Let's write it like this, x sub 1 equals, okay, the a0 we said is equal to 0, so we'll eliminate that one. And then we'll copy these various ones. So there's a1, put that in there for that. And a2, instead of this, and a3, instead of that one, and a4, minus sign. Oops, sorry, that was t cubed, going this way. And a5, and a6, and finally a7. Maybe off the page a little bit, but okay, and I'm going to define x1 to be that. And just so we can see it, let me wrap this around. So there is a solution of our cubic, which sort of has one of the solutions to the quadratic inside it. If C3 is 0, then we sort of reduce to the previous quadratic equation solution with just the Catalan numbers, which are the first elements in each of these brackets. But for the cubic, there's more terms, but we're only going up to degree 7. So I want to check whether this actually works. Okay, so we want to constantly use opportunities to check that what we've done is correct, because there's lots of ways of making mistakes. We can make logical mistakes, we can make algebraic mistakes, we can make cut and paste mistakes, and so on. All right, so let's go back up to the equation that we are trying to solve, which is our pleasant little cubic. There it is there. And let's check that. Okay, there it is there. This is going to be equal to, I'm just going to, okay, I'm going to just maybe over here, just replace the x with x1. That's the easy way of doing it, I suppose. Then we don't need this. Okay, and so let me just copy that. So it's just plugged this expression, the expression for x1. Let me just check what that looks like. So that's this thing that carries on here. I don't think you can see all of it, but anyway. And we've plugged it in for x1 here, and x1 here, and x1 here. We got these terms here. And now we want to kind of expand this and, you know, and simplify it. But to make life easier here, I'm going to just restrict to all our terms of degree 7 or less in t, so that we don't have to worry about all those higher powers of t, which would make this blow out. Actually, maybe let me illustrate that actually. So let's actually, just for fun, let me make a little bit of space here. Let's just expand this out. Okay, compute expand. It's a big polynomial in t. All right, and okay, we want to understand this, so let's have a look. add it as a polynomial in T. Just polynomial, collect terms, organize it in terms of T. What do we get? Well, there are all these higher powers of T, but notice the lowest power of T is T to the 8. What's that tell us? That tells us that this is equal to 0 up to degree 7. In other words, you make this big computation, all the terms involving t, t squared, t cubed up to t to the 7, including the constant term also, are all 0. Okay, so how should we don't need all this stuff here, so let's summarize that. Let's check that this thing here, okay, it does actually, it's equal to 0 up to degree 7. So we have, indeed, right here, let's put this, in a, display it. There we go. That is a solution. T to the 7, better not forget that one. That is a solution to our cubic equation, which is valid up to degree 7, expressing it as an on series in powers of t whose coefficients are rational functions of the CI, C1, C2, C3. And we see the Catalan numbers are involved, but there are other constants too. So a very big question is how to make sense of all these new constants and terms. But in any case, it really does appear as if we have now a new kind of solution to a cubic equation, quite different from that obtained by Del Ferro and Tartaglia and Cardano, etc. And purely in the algebraic world, without any square roots, cube roots, or any kind of other radicals that you can't actually calculate. So this is very exciting, but obviously we still have a lot more work to do to understand fully this cubic situation. I'm Norman Wahlberger. Thanks for listening.